This Lewis structure video is meant to be viewed along with the worksheet that has already been uploaded. You should be looking at the step-by-step instructions that I've already laid out. Today we're going to do some examples using those instructions. So it's kind of a good idea to be able to look at not only the examples we're going to do on the board, but also what those instructions are. So we're going to start with some basic Lewis structures and then get more and more advanced. And the first Lewis structure we're going to do is for CF4. Now the first thing, if Lewis structures are meant to display the bonding and the valence electrons in a molecule, we have to figure out how many valence electrons we're really dealing with. So we're going to count up the individual valence electrons from each of our atoms. We have 1 carbon, 4 fluorines. Carbon comes in at group 4A on the periodic table, so that's going to have 4 valence electrons. Fluorine comes in at 7. That's going to give us a grand total of 32 valence electrons. That's going to be important because we need to be certain that we're showing all of these valence electrons. The next thing we want to do is determine the central atom. Very few of these molecules have things laid out in linear chains. Instead, what you generally find is you have one central atom and then the rest of the atoms are surrounding that. So usually it's going to be the first atom that's listed. There's some exceptions to that. Hydrogen can't be the central atom, but usually you want to look at the first atom that's listed. Here we're looking at carbon. Carbon is going to be our central atom. We're going to put the fluorines around that central atom. I'm going to draw my fluorines around it. So now I have a central atom and the outer atoms determined. Next thing we want to do is there has to be something holding together all of these pieces. We might as well get those pieces in to this structure, to this molecule. We need to have at least one bond. So we're going to make a bond connecting each outer atom with that central atom. So I'm going to make a bond between the central atom and each outer atom. And the way we represent bonds in Lewis structures are just with lines. Okay? This line, every time we write a bond, really represents 2 electrons. There's 2 electrons being shared. That's what that line actually represents. 2 electrons being shared, 2 electrons being shared, 2 electrons being shared, 2 electrons being shared. We're only connecting the outer atom with the central atom. We're not connecting the outer atoms together. There's no bonding that's going to exist between these outer atoms. Our next step is there's sort of a magic number. You're going to see it's not really a magic number, but in many, many, many molecules, each atom ends up with a total of 8 electrons in its general area. So we're going to work on that part of it next, starting with the outer atoms. And the way we do this is we make what are called lone pairs. Now lone pairs are not bonds. They're not being shared. They belong exclusively to one atom. So when we look at this fluorine at the top, it already has 2 electrons in its area, the 2 from the bond. So to get up to 8, we're going to need 6 more electrons. We're going to put those in as lone pairs. Lone pairs look a little bit different than actual bonds. We represent a lone pair with a pair of dots. That's one lone pair. 2 electrons end up making a pair. So I'm going to need 3 lone pairs around each outer atom. So I'm going to do that around each of the fluorines. This fluorine, just like the previous one, has 2 from the bond. I need to bring it up to 8 by using lone pairs. So it's going to be 3 lone pairs here, 3 lone pairs here, and 3 lone pairs here. Each dot is a single electron, but we're always operating these in pairs. You're seeing we're almost always dealing with these electrons in pair quantities, in pair units. So now when we look at this, and there's several other techniques you can use to draw Lewis structures. regardless of the technique you use, whether it's this technique or a different technique, you really should be doing these next steps. These next steps pretty much guarantee that you have that correct Lewis structure. One of the first things we did is count up 32 electrons. We need to make sure that our molecule shows 32 electrons. If you're drawing a Lewis structure that's supposed to have 32 electrons and you don't have 32 electrons, then it has to be wrong. There's no choice but for it to be wrong. So we want to make sure we're showing the proper number of electrons. So we're going to count 2, 4, 6. Remember, these two from the bond are 2 electrons. 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We have 32 electrons. There's a second check that we need to make on this. That second check that we need to make on this involves that octet rule, that 8 electrons around these atoms. We're going to see some things aren't going to follow the octet rule like hydrogen, but here we're going to start looking for 8 things around each atom. So I'm going to start with the fluorine. This fluorine, 2, 4, 6, 8 around it. 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 You want to check the central atom as well. That central atom, the carbon, 2, 4, 6, 8 around it. Each of our atoms has 8 electrons around it. It's satisfying the octet rule. We also have the correct total number of valence electrons. So this is going to be the correct Lewis structure for that. So we're just going to do example after example in this video so we can actually see what's going on with Lewis structures, and you want to be able to write Lewis structures flawlessly. The reason why you want to do such a good job writing Lewis structures flawlessly is in this unit, Lewis structures are relatively straightforward compared to some of the other parts, but it's essential going on to the next parts. Like if you're not writing a Lewis structure correctly, everything that we're going to do after Lewis structures just isn't going to work out right. So in this one, we're just going to keep on drawing Lewis structures and get more and more involved Lewis structures as we kind of go through this. Next molecule I want to do is NF3. Same thing. First thing we want to do, figure out how many electrons we're dealing with. I have 1 nitrogen, 3 fluorines. Nitrogen comes from group 5A, so I'm looking at 5 valence electrons. Fluorine comes through group 7A, so I'm looking at 7 valence electrons. Sum up all of the valence electrons, we're going to get 26 total electrons that we're actually needing to deal with for this. Next, determine the central atom. Usually it's the first one listed. Again, hydrogen's not going to be the central atom. We're going to actually see some examples of hydrogen in a little bit. So we're going to start with nitrogen as our central atom. We're going to put the fluorines around that central atom. And it doesn't really matter where you space them out. I'm going to put 1 here, 1 here, 1 here. You didn't have to put them in that orientation. You could have put 1 here, or 1 here, or 1 here. You could have made them equally spaced out. It doesn't ultimately matter when you draw the Lewis structure. When you draw a 2-dimensional Lewis structure, that in and amongst itself is not trying to convey how the molecule looks in 3 dimensions. For the entire rest of the chapter, that kind of key part that we're going to deal with is we're going to take the information from these Lewis structures and show how they actually look in 3 dimensions. But just your flat Lewis structure doesn't need to look like how it's actually going to look in those 3 dimensions. So now, something has to be holding these pieces together. So I'm going to make a single bond connecting each outer atom with that central atom. Now I'm looking at completing the octets on those outer atoms. Each outer atom only has 2 electrons, the 2 from the bond around it. That means 3 lone pairs to bring up to 8 electrons. So I'm going to make 3 lone pairs on each of these fluorines. Now I'm going to do my checks again. I'm going to check how many electrons I actually have in my structure. I need 26. I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And I have 24 electrons in my structure right now. I need 26. This is definitely not the correct structure yet. I need to make some changes. This check fails. If this check fails, don't even bother doing the second check for the octet rule. You have more important things to do. You got to fix the total number first before you can start worrying if things are following the octet rule. One way of thinking about it is if your car's outside and you're going to try to start your car, if your car doesn't start, that's a bigger problem than your windshield wipers maybe being a little bit streaky. You need to fix the bigger problem before you worry about minor problems. For us, the biggest problem is our car's not starting. We don't have anywhere close to the correct number of electrons. So we have to fix that. I have 24 in my structure, I have 26. If you're following along that worksheet of instructions, what you're going to see is it's at this point when we need more electrons. I need more electrons in this structure. I've taken care of the bonding. I've taken care of lone pairs on the outer atoms. It's at this stage that we can start adding lone pairs to the central atom, not before. But this is the stage we can actually do it. I need 2 more electrons, and at this point, they go on the central atom. So even though on that worksheet I'm past those 2 checks, these last 2 checks are going to be the last things you want to do. They pretty much guarantee that you've done this problem correctly. So I'm going to go back and double check things. I need 26 electrons. Do I have 26? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. I have 26 electrons. What I didn't do the first time through is I didn't check the octet because I had a bigger problem that we had to fix first. That was the total number. You better go back and check those octets as well because that's also going to be important. This fluorine, 2, 4, 6, 8. This fluorine, 2, 4, 6, 8, following the octet. This fluorine, 2, 4, 6, 8, following the octet. The nitrogen, 2, 4, 6, 8. Everything has its octets. Being everything has its octets, and I have the correct total number, this is going to be the correct structure for NF3. So you can continue doing this with more and more and more molecules. What you're starting to see though is in the instructions you have hydrogen being the exception a lot of times. And hydrogen is such a common atom in compounds. I want to next do a couple of examples that show you how to actually deal with hydrogen in these compounds. And the first one I want to do with that is SiH4. Just like before, you have to know how many electrons you're really needing to deal with here. So I have 1 silicon, 4 hydrogens. Silicon comes in group 4A for 4 valence electrons. Hydrogen comes in group 1A for 1 valence electron. My sum total that I'm looking at 8 total electrons that I need to deal with. Determine the central atom is the next step. Usually it's the first one listed. We also know that hydrogen can't be the central atom, so right away we only have one choice for that central atom. That's going to be the silicon. The hydrogens are going to be the outer atoms. I'm going to get the 4 hydrogens in. There's got to be something connecting, bonding each outer atom to that central atom. So I'm going to go ahead and get that bond in, making a single bond between each outer atom and the central atom. Now ordinarily at this stage I'd work on completing octets around each of those outer atoms. Well, hydrogen's the exception. Hydrogen doesn't get an octet. Hydrogen can't handle 8 electrons. Hydrogen can only handle 2 electrons. So most elements are following the 8 electron rule, sometimes called the octet rule. Hydrogen though follows what's called the duet rule. 2 electrons around hydrogen. So when I look at the hydrogen, each hydrogen already has 2 electrons around it. It can't handle any lone pairs. Do not stick any lone pairs in there. So now I'm just going to go on to the next step, because I'm not putting octets in for the outer atoms because they're hydrogen, they can't handle it. I'm looking for my total number of electrons. Do I have 8? 2, 4, 6, 8. I have the 8. I still need to check for the octet rule. We know hydrogen won't follow it. Hydrogen only follows the duet rule, and each one does only have 2. But silicon needs to follow that octet rule. So I need to make sure silicon has its 8 electrons. So I look at silicon, 2, 4, 6, 8. Silicon has its 8 electrons. I have the correct total number. I'm satisfying the octet rule for those things that need the octet rule satisfied for. This is going to be our correct structure for this. I want to do another example that involves hydrogen. Pretty common molecule, we're familiar with it. I want to do water. So H2O. First step, always figure out how many valence electrons you have. Here I have 2 hydrogens, 1 oxygen. Hydrogen's in group 1A for 1 valence electron. Oxygen's in group 6A for 6 valence electrons. That's going to give me a total of 8 valence electrons. Determine the central atom. Usually it's going to be the first one listed, but there's exceptions. Hydrogen's the exception. Hydrogen doesn't follow the octet rule. Hydrogen also can't be the central atom. It can't handle that many electrons around it, therefore that can't be the central hub tying this molecule together. So if it's not hydrogen, it had better be oxygen. I'm going to get oxygen in the middle, hydrogens as the outer atoms. Make a single bond connecting each outer atom to that central atom. Next, we would complete an octet of electrons around each outer atom. Outer atoms are hydrogen though. They're not going to get the octet, they're only going to get a duet, and they have those too. So I'm going to check and see where we're at. Total number of electrons, 2, 4. I don't have the 8 I need. This is definitely going to be an issue. I don't have the 8. Well, what am I going to do? I'm going to start adding lone pairs on that central atom. So I need 4, so that would be 2 pairs on that oxygen. Now I'm going to go back and do both checks. The last thing you should do in any Lewis structure that you're writing is to do these checks. I need 8 electrons. 2, 4, 6, 8. I have 8. Now I'm checking for octet and duet rule. Hydrogen follows the duet rule. It has 2. Hydrogen has 2. Oxygen 2, 4, 6, 8. Here's our correct Lewis structure. Now for Lewis structures aren't meant by themselves, solely by themselves, to convey the three-dimensionality of the molecule. Water is actually not a linear molecule like this. Water actually, in 3 dimensions, would look much more like this. And that's something we're going to talk about when we get into the next chapter. The next chapter is pretty much taking a Lewis structure and actually getting it into how is that really going to look in 3 dimensions. Next one I want to do is SO2. SO2 is sulfur dioxide. SO2 is kind of a component of, goes into leading into acid rain. You often get SO2 from the combustion of coal that has a high sulfur content. That puts SO2 kind of into the atmosphere. So SO2, I have 1 sulfur, 2 oxygens. Sulfur is in group 6A for 6 valence electrons. Oxygen is also in group 6A for 6 valence electrons. So I'm looking at a total of 18 electrons I need to deal with for this molecule. Next up, I'm going to determine the central atom. Usually it's going to be the first one listed. So I'm looking at the sulfur. I'm going to make oxygen my outer atoms. Now I'm going to complete an octet of electrons around that outer atoms by making lone pairs. So each oxygen is going to get 3 lone pairs. Now I'm going to check and see how I've done. I need 18 electrons. 2, 4, 6, 8, 10, 12, 14, 16. I only have 16 electrons in my structure, so this is definitely not going to be the right structure. I need 2 more electrons. Where are they going to go? They're going to go as a lone pair on that central atom. So now I'm going to go back and do these checks again. I need 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. I have my 18 electrons, but one thing I didn't check first time through was that octet rule. So I better go back and do that now. This oxygen, 2, 4, 6, 8 electrons around that oxygen. That's good. This oxygen, 2, 4, 6, 8 electrons around that oxygen. That's good. But when we look at the sulfur, 2, 4, 6, I don't have an octet around the sulfur. I have the 18 electrons, but I'm not satisfying the octet. Now what I can't do, I'm going to do this in red, you can't just throw 2 more electrons on the sulfur and say, oh, sulfur's short, let me give it some more electrons. Because if I tried to do this, what would happen? I'd be at 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I wouldn't have the correct total number. I went from a bad situation, I made it worse. So I can't just throw in more electrons. That would give me the incorrect number. Instead, I need to rearrange what I actually have in place. I have the correct total number in here. They're just not arranged correctly. So this is kind of that last step you're seeing on that worksheet. That last step says, okay, if you have the correct total number of electrons but you're not satisfying octet rules, what you need to do is take a lone pair from one of the outer atoms and make a multiple bond with that central atom. So it doesn't matter which outer atom you pick or which set of electrons you pick. You're basically just going to take 2, and I'm going to show this result, and take these 2 electrons and bring them in to make another bond between the sulfur and the oxygen. So I'm going to go ahead and redraw the result of that. I'm going to leave everything else exactly how it was. So what do I have? I just made a bunch of changes. There's no reason to know or to be unsure if you have the correct structure or not. There's 2 real easy checks you can make sure that you're dealing with the right structure. So let's go ahead and do those. 18 total electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18. I have 18 total electrons. That's good. Now let's check the octet rule. Remember, I was failing the octet rule on the top. Let me see if I'm following it here. This oxygen, 2, 4, 6, 8. That's good. This oxygen, 2, 4, 6, 8. That's good. The sulfur, 2, 4, 6, 8. That's good. So here is our correct structure. I have the correct total number of electrons. I'm also following the octet rule. Now this molecule brings us into kind of something else that we need to talk about. And that's the idea of resonance. When we looked at this, we had a choice of which ones we could bring in. And this shows one of the limits of Lewis structures. Okay? Lewis structures use dots and lines to represent electrons, which we know are pretty complex. Dots and lines are simplest form of written communication. Tens, maybe hundreds of thousands of years ago, that was the first form of written communication. That's what cave people did. First form of communication was a dot. Second was a line. Now we're trying to use these to actually show what's happening with electrons, and we're seeing we're having a little bit of a limitation in terms of actually doing that. And here's why this is a limitation. This structure we just wrote, even though it follows the rules, is not a good representation of what's happening in this molecule. In this molecule, it's showing that the oxygens are truly different. One of them is doubly bonded to the sulfur, one of them is only singly bonded. So if you have more bonds, you're sharing more electrons. Here, 2 electrons in each bond. Here I'm showing 4 electrons being shared here and 2 electrons being shared for the one on the right. What happens is when atoms are sharing electrons, the more electrons that are being shared, the closer those 2 atoms can get. Okay? They're sharing more. There's more holding them together. Kind of the cause and effect is different, but you can think about this the same way you do your friendships. Your best friend, you're very, very close to. They know an awful lot about you that some of your casual acquaintances don't know. You're closer to them. You share more with them. So this is showing there's a different relationship the sulfur has with these oxygens based on our Lewis structure. But that's just not true. When we look at SO2, we can measure the distance each oxygen is away from the sulfur. And what we see is that they're actually equally spaced apart. So that doesn't match our actual Lewis structure here. And that's because sometimes a single Lewis structure does not do a good enough job in showing what's actually happening with molecules. Remember, we're using simple written communication here, dots and lines. Sometimes that doesn't get the job done. So I want us to go back to the top where I said it didn't matter which ones you kind of used. Well, let me just explore the situation where instead of using the one on the left, I'm actually using the one on the right. If I would have, instead of bringing these in, if I would have brought that set in red. If I would have done that, I would have gotten a slightly different looking structure. I'm going to draw this on the bottom. If I move the red electrons in, I would have gotten this structure, a little bit different. Neither one of these structures that I wrote, let's just label them, structure A, structure B. Structure A is no better than structure B, structure B is no better than structure A. Neither A or B really show what's happening with this molecule. They're both hinting at something that's not actually true, that there's a difference between the bonding of the oxygens and the sulfur. So what it really takes is both of these combined in order to accurately display what's happening with the molecule. And that's the idea of resonance. Resonance is when it takes more than one Lewis structure to accurately portray what's actually happening with the molecule. So we would say that these are resonant structures of each other, or they're a resonant set. And there's a relationship that these have. To show that we need both of them and that they're related, sometimes we put an arrow in to show we need both of these. Now here's the common misconception about dealing with resonance structures. The common misconception is, oh, it's just switching really quickly back and forth between A and B. It's A, then it's B, then it's A, then it's B, then it's A, then it's B. No, that is not how this actually is happening. This molecule never looks like structure A. This molecule never looks like structure B. They are not switching back and forth. Instead, the real structure of SO2 is really a perfect averaging, a perfect combination of these two structures. It's going to look at that average of A and B at every moment in time. It's never going to look like A and it's never going to look like B. It's going to look like a combining of those. I kind of have a non-chemical way of thinking about it. Where I used to live, guy a couple houses down had a dog. Okay? Very, very ugly dog. Now, I like dogs. I have a dog. Kind of always have had a dog. But this dog, even if you like dogs, you're like, man, that's not an attractive looking dog. But I'm trying to be neighborly. So I say, hey, great dog. What is it? Well, the guy turns to me and he says, well, it's half German Shepherd, half Beagle. Now I want you to take a moment and think about what this dog looks like. There's a reason that those two breeds of dog are not intentionally bred together. You're not going to see that in the American Kennel Club dog show anytime soon. It doesn't result in a good-looking dog. Now, I used to have a Beagle. Great little dog, big voice. Okay? German Shepherd, nice, stoic, large, handsome dog. They're both very attractive dogs in their own right. But the combination does not work. Now this half German Shepherd, half Beagle, it would have been cool if it changed from looking like a Beagle to a German Shepherd, to a Beagle, to a German Shepherd, to a Beagle, to a German Shepherd. That would have been cool. That's not what happened. Instead, it was a perfect combination of those two breeds at every moment in time. It's a perfect averaging. Just happened that perfect averaging was not very attractive. So it was 100% ugly 100% of the time. It was never switching back and forth. Instead, it always looked like that complete combination, that complete averaging. And that's what we're seeing here. We're not seeing this switch back and forth. It's not switching back and forth because it's never one of these to begin with. To really view the true structure of SO2, we need a perfect combination of these two structures. It takes a resonance set or a resonance series in order to actually explain it. It's really an averaging of both of those structures. I want to do a couple more in this first video. And the next one I want to do is this works, this Lewis structure writing works not just for molecules, but it also works for some of your polyatomic ions as well. So if I have something like, I don't know, nitrate ion, I can actually draw the Lewis structure for this. Because even though this is an ion, these individual pieces are being held together covalently. So I'm going to deal with this one the same way I've dealt with the other ones. I have one nitrogen and 3 oxygens. Nitrogen is in group 5A, oxygen